agreement. This paper targets the problem of accountability, which is the problem of detecting a certain fraction of a malicious coalition that led to a safety violation of a distributed protocol. In our particular case, we deal with consensus protocols. First, we will quickly present the consensus problem with its inherent limitation. Then, this limitation will motivate the introduction of the notion of accountability. Thereafter, we will explain how we can reason on proof of culpability with message justifications and why there is an inherent problem with the fault detection with this approach. Finally, we will see the example of executions of PBFT protocols that are not accountable. The consensus is one of the most well-known problems in distributed computing, where the task to be solved is agreeing on a common value. Every process proposes a value as input and is supposed to eventually decide a common value as output. The agreement property consists in the fact that all the correct processes decide the same output. By correct, we mean that the processes follows a dedicated protocol. We also add a validity property to avoid trivial solutions where every correct process decides always a pre-established value. Typically, a validity property can be if all the processes are correct and propose the same value v, then the decided value is v. Because of the FLP theorem, no fully asynchronous and deterministic distributed protocol can solve the consensus problem and tolerate even a single crash fault. Thus, any solution either uses randomization or assumes a form of synchrony. Today, we focus on partial synchronous solutions. A frequent question is how many Byzantine processes can be tolerated by such an asynchronous solution? And the answer is n/3, where n is the number of participants. In fact, this bound can be applied to the majority of asynchronous Byzantine distributed programs. This is problematic for critical applications like blockchain that depends on such a Byzantine consensus algorithm, and even more so if the participants have good incentives to tackle the safety property, typically performing a double spending. Hence, it is natural to try to obtain some new properties in a degraded scenario where the number of malicious processes t is greater than n/3. But for the same reason of the n/3 bound, we can't obtain a protocol that both solves consensus when t is lower than n/3 and preserves safety if t is greater than n/3. This is why we are interested in an accountable protocol that ensures both liveness and safety when t is lower than n/3, but also eventually detects n/3 Byzantine processes in case of safety violation. We assume that all the messages are signed with an encryption chain which ensures non-repudiability. That is, if Charlie delivers a message M authenticated to be from Bob, Bob indeed sent M to Charlie and can't deny it. During the execution of the protocol, the processes send and receive some messages which can be stored. So all the processes collected individually some sets of pieces of information that are signed messages, and collectively they collected the union of the sets. Because of the encryption, nothing prevents them from centralizing those pieces of information by exchanging them. After such a centralization, the correct process can try to compute a proof of culpability against some potentially Byzantine process that would have performed a commission fault, which consists in sending a set of messages that is not supposed to be sent. This task would be trivial if all the commission faults consisted in sending a set of conflicting messages that are not supposed to be sent together. But unfortunately, this is not the case. Another kind of fault consists in sending a message without having received a proper justification. We call such a fault an evasion fault that has been formalized in a parallel world to be released. In a distributed protocol, sending a message is allowed almost systematically only if some other messages have been previously received. We present this notion with a dependency graph. Here, the message M0 is allowed to be sent by the process Charlie if Charlie received the messages M1, M2, and M3. We say that M1, M2, and M3 are justifications for M0. The content of the message M0 can also be a function of the content of the messages M1, M2, and M3. Hence, it is possible to define a direct acyclic graph of dependency. A modification in a node of the graph can impact all the graph by domino effect. Here, the modification of M4 into M4 prime causes indirectly the modification of M0 into M0 prime. Thus, a fault introduced somewhere can have an impact far away from its introduction. The problem becomes the identification of the source of the error. Here, if Charlie eventually realizes that something wrong happened, he can't say if the source of the error is Alice or Bob. Moreover, if the senders of Alice and Bob are accomplices, they can be mute forever and cover each other so that without synchrony assumption, the receiver of M1 prime can't say who is the culprit. A counter strategy could be to ask to broadcast each message sent to a particular node before making progress, but here again, some indistinguishable scenarios appear. The last solution is to ask to attach the justification in its message. Typically, we would transform the algorithm so that the message M1 has to additionally encapsulate the received message M4 and M5. But the problem is still present if the deepness of the justification chain is limited. Here again, if the message M0' encapsulates M', M2, and M3, Dave can't say if the source of the error is Alice or Bob, because it doesn't have access to the message M4. So the justification-based solution should encapsulate all the causal graph, but it can be very expensive. Now we will present the example of PBFT, which works in every PBFT-like protocol when the number T of Byzantine processes is greater than 2n/3. PBFT relies on a leader that rotates in a round-robin fashion across views and proposes a suggestion in its view. Two local variables per process, preparation and decision, have values that relate with each other, such that a decision value always requires the same preparation value from 2n/3 distinct processes, including itself. During view changes, a preparation implies a propagation of this value to the leader within message announcing the new view. A suggestion value in view v plus 1 must be proposed by its leader and correspond to a preparation motivated by 2n/3 messages sent in view v. If t is lower than n/3 and the new leader is correct, the new suggestion is the prepared value propagated with the fresher view number. In fact, a suggestion encapsulates a proof that this is the prepared value with the fresher view number. However, if t is greater than n/3 and the new leader is faulty, it is possible for him to propose a value prepared at view vx, while a different value has also been prepared at view vy, with vy strictly greater than vx. The concurrent fault is the propagation of an outdated prepared value during the view change. The question is, who performed this fault? Here, this is Charlie who prepared a certain value that will be decided by Bob, but propagated an outdated one that will be eventually decided by Alice. And here, this is Dave who performed the said fault. When t is greater than 2n/3, it is possible to construct two executions with different set of Byzantine processes that can't be distinguished by the correct processes. In fact, this is the leader Ev who stored the crucial pieces of information to distinguish the two executions. But if Ev stays mute forever, then we can't distinguish the executions. If we ask for justification with a certain degree of depth, then we can perform the same kind of attack with a chain of d plus 1 malicious leaders that cover each other. Thus, it becomes costly to detect who propagated the outdated preparation. To avoid such a cost, we need to design an algorithm so that a safety violation can't be performed with a chain evasion fault with a too high degree, and that's what we did. To get more details, you can read the paper. Thank you very much.